The standard model of particle physics, with its quarks, leptons, and bosons, has served scientists incredibly well since it was first put forward in 1967. For the most part, it has correctly predicted the existence of particles with such precision, it's often hailed as the most successful scientific theory of all time. And yet, scientists are not done with it, and they're constantly probing around its edges hunting for new particles. In fact, several teams of scientists are racing to discover what's known as a Majorana fermion, which could be a major key to settling some of the universe's biggest mysteries. Fermions are matter particles, like the quarks that make up protons and neutrons, as well as electrons and neutrinos. Fermions also include corresponding antiparticles with very similar properties, except they have opposite charge. So the antiparticle of a negatively charged electron has a positive charge and is known as a positron. Should a particle and its antiparticle meet, the two will annihilate each other, leaving behind only energy. But a Majorana fermion would play by its own rules that could totally upend our understanding of the standard model. In theory, a Majorana particle doesn't have a corresponding antiparticle, it is its own antiparticle. That means when two of the same particles meet, they could wipe each other out. So, where would we even begin to look for a Majorana particle? As it happens, scientists have already identified a candidate from the standard model, the neutrino. Neutrinos are bizarre little things for more reasons than just their famous ability to pass right through whole planets. Unlike electrons and positrons, which both can have right or left-handed spins, neutrinos all have left-handed spins, while antineutrinos are all right-handed. To explain this, one idea is that maybe antineutrinos aren't antimatter after all, they're just all the missing right-handed neutrinos. Speaking of missing matter, if neutrinos are Majorana particles, they could account for that too. One of the great mysteries of the universe is why there's, well, anything. There's no reason we can solidly point to that explains why there's more matter than antimatter today. There's nothing inherently special about matter, and it probably formed in equal amounts with antimatter after the Big Bang. So that means by now, everything should have been annihilated. And yet here we are, made up of and surrounded by regular matter, not getting spontaneously annihilated all the time. But it's possible the imbalance is the result of a particular way some atoms decay. Beta-minus decay is when a neutron in an unstable nucleus decays into a proton and emits an electron and an antineutrino. An extremely rare event known as double beta decay occurs when certain nuclei have two neutrons decay simultaneously. You see where I'm going with this, right? If a neutrino and an antineutrino are actually the same particle capable of annihilating itself, then sometimes double beta decays will emit only electrons. This net gain of particles could help account for the imbalance between matter and antimatter. Of course, theorizing about Majorana particles is one thing. Actually finding evidence of them is quite another. While neutrinos are notoriously hard to spot, neutrino-less double beta decay should be detectable just by adding up the energy of the resulting two electrons and isotope. Really, the problem lies with luck and timing. Remember I said that double beta decay is rare? Well, a double beta decay where the neutrinos annihilate each other should be at least 100 times rarer. That doesn't mean scientists aren't still trying to spot it. The preferred approach involves getting a huge amount of an isotope capable of double beta decay and just waiting. There are multiple experiments active and planned using elements like germanium and xenon. They need to keep the background radiation and the energetic movement of the atoms from ruining the data, so many of them are shielded and kept cold. Like the Cuore experiment in Italy, which is just 0.01 Kelvin above absolute zero. What's cooler than that? Well, maybe the fact that it's protected by 4 metric tons of lead recovered from a 2,000-year-old Roman shipwreck. Seriously, the scientists had to borrow it from a museum. If these experiments don't see signs of neutrinoless double beta decay, then maybe it's even rarer than predicted and even bigger tanks of decaying isotopes will be necessary. Or maybe it's not possible at all and the Majorana particle is a dead end. Or, if luck is on our side, maybe we'll see the telltale sign of two neutrinos erasing each other, and the Standard Model and our understanding of the universe will get a little bit more complete. Fun fact, Majorana fermions are named after Ettore Majorana, a physicist who mysteriously disappeared without a trace in 1938. So, about the whole Standard Model being the most successful scientific theory of all time. Turns out a recent discovery has thrown a wrench in that. Amanda has a view on that here.